All right, this is the third time we've looked at section 3.1. It's a very long section. And the last thing that we left off on last time was talking about some different number systems, not because they're the only ones that exist, but because they gave us some perspective on how we can look at any number system. So we specifically looked at numerals in base 3, 7, and 12. And so we're going to do a couple of examples now where they look a lot like the ones we did with the Mayan and the Babylonians and so forth, where we say what comes before, what comes after. Here's the thing. When they ask you these, usually one of them is really straightforward and simple. Right? Either the taking one away or the adding one to it's just a no-brainer. The other one usually requires you to do some kind of borrowing, regrouping, right? Or some kind of carrying with regrouping. And it makes things a little bit more challenging. So as we're taking a look at this first one, I've got the value that's 1, 4, base 5. So which one's the easy one to do? Taking one away from it or adding one to it? Taking one away. So if you're not sure why that's easier, let's do the taking one away, and then we'll see why the adding one to it makes it a little bit more challenging. So the 1, 4, base 5 is the one that's in the middle. What comes before 1, 4? 1, 3. And we are going to write the subscripted word 5 every time we do that, okay? 1, 3, base 5. What happens if I take the number 1, 4 and I add 1 to it? I can't get really 1, 5, right? Like that would be our inclination, right? Would be to write down 1, 5. But what about 5s in base 5? They don't exist, right? There are no 5s in base 5. So I've run out of 1's digits in base 5 when I hit the number 4 in the 1's place. So what do I do when I've run out of digits? What comes after 1, 4? It's 2, 0. Yeah, so we go 2, 0, base 5. It's very similar to asking what's after 19, right? It's 20. It's a 2 in the 10's place and a 0 now in my 1's place. The same idea. Okay, how about the number T0, 0, base 12? Which one's the easier one to do? The one before or the one after? Oh, the after one's easier on this one. What comes after T0, 0? T0, 1. Yeah. But when we try to take 1 away, we're trying to take 1 away from 0 here, right? Everybody agree with that? That's not a very straightforward thing to do, right? I can't just take 1 away from 0. That doesn't work. I have to do some regrouping, or you might have heard of it as borrowing. And I can't regroup it from the next one either because it's just another 0, right? I have to go all the way over to the T value to do the regrouping. Now, what does T stand for in our base 12 system? It's the number 10. So if I take 1 away from the number 10, what will it become? It will become a 9. And then I add that 1 to the middle column here. But how many am I regrouping or borrowing when I'm in base 12? We're borrowing or regrouping the number 12. This is what we do in base 10, right? Let's just change it into a number that you're familiar with. If you had the number 800 and you changed the number 7, the 8 to a 7, what would you put here instead of the 0? 10. You'd put a 10. We're going to change it to a 9 in a second, but you'd put a 10. Right? We're borrowing 10. This is the number 100. If I take a $100 bill and I break it into tens, how many tens do I have? 10 tens, right? So I'd get 10, and then I'd have to borrow again or regroup again. This 10 would become a 9, and then this 0 would become a 10. Okay? And then we'd do some sort of subtraction or whatever we need to do at that point. I haven't subtracted anything. I've just regrouped. Okay, so coming back into our number that we're working with right now, when I borrow in base 12, I borrow what number? I borrow 12. Whatever base you're in, if you're borrowing or regrouping, that's the number you're borrowing or regrouping. How do we write a 12 in base 12? Well, if you want to just write 12, you can. If you wanted to write the W, that's what we would have. It would be a W. So let me write the 12 down because I think that might help us for the moment. There's 12 there. I need to borrow from the 12. If I borrow from the 12, what will I borrow? Let me do that first. What will I borrow? I'll borrow 12. And then, so I take 1 away, so I borrow the 12. And then the 12 that I've borrowed from becomes what? an 11. Okay, so this number has been regrouped into a 9. This is the 2-digit number 11 and the 2-digit number 12. But the goal was to take it away. If I take, sorry, it looks like this is my answer. It's definitely not yet. Let me shift this down. I'm doing some work. If I take one away from my 12, then it will become an 11. So if I take one away, because that's what we're supposed to be doing, we're supposed to be finding the one before it, so we take one away. I've got a 9, and then an 11, and then an 11. Okay, that's the number I've got. But I can't put 2 digits in a single placeholder. So I use a symbol that represents the word, or the number, 11, and that's our symbol, E. So this one would be a 9, followed by an E and an E in base 12. It is kind of confusing, I agree. So think about it. You know how to do this in base 10. You've done it for at least 12 years. You usually run into it in about 2nd grade, sometimes 1st grade. Into 1st grade, it depends. So you've done it for, give or take 12 years. So how do you think that 1st grader feels when they're trying to take things and they're borrowing and they're turning 10s into things, they're putting in a single digit place, and they're supposed to have 2 digits, and now I got 1 digit, and it's confusing, right? It's not a super direct sort of process. We will talk about subtraction. It's actually in section 3.2, and some other methods that are not regrouping that can sometimes help students when they're struggling with that concept. Let's talk about conversions. I think those are a little bit more straightforward than looking at the number forward and backwards. So if we are converting, we're going to be converting in and out of our number systems. So this is converting some number system, whatever, into base 10. We're going to put the numerals in expanded form, and then we're going to multiply out the expanded form. So let me give you an example of what that means. It doesn't take a lot of space, but if I had the number 517, and I was in base 8, this number 5, this number 1, and this number 7 are all place values that are of value 8. So this 5 is in the 8 squareds place. The 1 is in the 8s place. And the 7 is in the 1s place. So this right here is the expanded form that it's talking about. It's saying use the place value you're in. This one I chose to create was base 8. And do powers of 8 that you're multiplying by. Okay? And then step 2 is simply to multiply that out. So let's do an example of one that we're actually going to do. This one is 1001 base 2. So we've got the number 1. It's going to be multiplied by something. We've got a 0. It's going to be multiplied by something. And I know 0 times anything is 0. We're just using it as a placeholder. Okay? So if you look back at this later, you're like, why did I skip all those steps? We didn't. We're going to write the zeros in their place values. Okay, so each of the numbers from the number that I was given, 1001, are represented there. Does everybody see that? Okay, but I'm in base 2, which means I'm doing powers of 2. Let's start on the right-hand side. The right-hand side is always the number 1. The reason that's the case is because anything to the power 0, okay, like 2 to the power 0 in this case, would be equal to 1. So this is always the 1s place. The next one is always the base that we're working in's place, base 2. It's base 8 on the previous example I mentioned. And then we do powers of that. So this is 2 squared. And then it would be 2 cubed. Yeah?
So on this one, you're putting the exponents inside the parentheses?
It doesn't matter. You can put them either place. It doesn't affect it. Yeah. Yes?
Do you always work, like after that would be to the power 4 to the power 4?
It would. Yeah, all the powers would just keep increasing from there if we needed more of them. Exactly. Yeah, now some of these are not very exciting, admittedly. Right, like this is 0 because I'm multiplying by 0, and this one is also 0. Right? Those are very unexciting values. What is 2 cubed? 8. 2 cubed is 8, and then 8 times the one in front of it would be an 8. And on the end, 1 times 1 would be 1. Does So what do I get if I add 8, 0, 0, and 1 together? This is the number 9. That's our number 9. If you wanted to be very clear to try to further emphasize it, you could put 9 with the little subscript and write the word 10 out. We're working in base 10. But it's understood to be base 10 if it's not written. So it's okay that we write it just as 9. Okay, so the next one is T00. Maybe I should do some examples without so many zeros. Sorry about that. So T, what is T's actual numerical value that we think of? It's a 10. T is 10. So this is 10 times some number plus 0 times a number and another 0 times a number. Start at the right, just to remind ourselves there's always a 1 here. And the next parenthesis is the base that we're in. What base are we in?
12.
We're in base 12, so it's 12 that's going to go in there. And then what goes in the next parentheses?
12 squared.
12 squared, exactly. All right, so again, not very exciting in some ways because 2 of these end up being 0. But the other 2 don't. All right, the other 1 doesn't, excuse me. So what's 12 squared? 144. And what would be 144 times 10? Write that, 1,440. And if I add these together, again, not a lot going on with the addition, but we get 1,440. Okay, so that's moving from some other random system into our system. Okay, so these aren't great examples. Let me actually go back to the one that I sort of made up here and kind of give you a visual imagery again. We've done this before, but I want to do it again. 517. So the expanded form tells you, like my Lego example, that's what I'm going to use. Okay, the 5 at the beginning tells you that there are 5 bags of 8 squared Legos in. So there's 5 bags of 8 squared, that's 64. So 5 bags of 64 Legos. Okay. The middle one tells you there's 1 bag of 8 Legos. And the last one tells you there's 7 left over. And what's sort of imagery-wise happening is that we take those 5 bags of 64 and that 1 bag of 8 and then the leftover 7, and we dump them all on the floor and we count them. And if we count them the way we've always, sort of regrouped and counted in base 10, we will get the number of Legos in our base 10 number. Okay? So we're going to go backwards now. We're going to turn our number into some other base number. So the same situation applies. We're going to come dump the Legos, but we're not going to put them in groups of tens and hundreds. We're going to put them in groups based on the place value we're working in. So we're going to consider the expanded form for the base. I'll show you what that means when we do one. And then we're going to use the division scaffold. Now we've used division scaffolding for 2 problems. We used it for Babylonians and we used it for Mayans. It's the thing where we were dividing and we had it kind of looks like a top hat. There's a number in the middle and we put the division factor on the left and we tell it what divides by on the right. That's what the division scaffolding is. Okay, so here's our example, first one. I have 11,028. That's actually 11,028, and we're turning it into base 4 things. So what I need to do is I need to figure out what are the base 4 powers. Like that's what I need in order to make this work. So we're going to work from right to left because that's how we're going to think about them. I have the 1's place, and then I have the 4's place, and then I will have 4 squared. So what is 4 squared?
16.
It's 16. And then I'll have 4 cubed. What's 4 cubed? 64. And then I'll have 4 to the 4th. What is 4 to the 4th?
256.
256. You might be thinking, when am I going to stop? We're going to stop when we get a number bigger than 11,000, okay? That's how far we're going to go. Okay, I'm going to have 4 to the 5th.
Is it 1024?
I think that sounds right. 4 to the 6th.
4096.
And if I do 4 to the 7th, what happens?
You said 4096.
I said 4 to the 7th. Which one are you looking at?
4 to the 6, is it 4096 or 4069?
Oh, I have a typo. 4096 is what I meant to write down. Thank you. Oops. Thanks, Ty. 4096, and then 4 to the 7th is 16,000 something.
So 16,384.
Okay. So at the point where I get something too big, that's the value I don't need. All the values before that, right, 40, 96, 10, 24, and so forth, all those values are going to show up in my division scaffolding. And we're just going to go down the line one at a time. Okay, just down the line one at a time. So we're going to start with 40, 96. And we've got the number 11,028. And our calculators are support with this, right? We're going to do it with a calculator. So what is 4096 into 11,000? How many times does it go in? It goes in 2 times. What is 2 times 4096? And then we're going to subtract. So what is 11,028 minus 8,192?
It's 2,836.
Thank you, 2,836. So we're just going to kind of mark them off as we go so that we know that we've done them. So we've taken care of the 4 to the 6th, which is the 4096. Now we're going to divide by 1024.
It's 217.
Okay, so it went in 2 whole times, so it's 2 times 1024.
2040.
48? Yeah, 2048. Okay, good. And so when we subtract, what does that give us? $788? Okay. And then what will be the next thing I divide by?
256.
Yep, now we're going to divide by 256. So how many times will 256 go into 788? 3 times. We don't always get 2s. All right, so what is 3 times 256? That's too small. Oh, okay, that makes more sense. Thank you. Okay. So if I subtract that one, I think I'm at 20. Am I right? Is that right? Yeah. Okay. So it's really tempting. So I've done this one. It's really tempting to skip over the 4 cubed, which is 64. Do not skip over it. It still needs to be in there. It's a very unexciting step, but it still needs to be in there. Because how many 64s are there in 20? 0. And that 0 is part of our expansion of numbers. It is part of our answer, so we need it to be present in that list. And of course, 0 times 64 is 0. So I get a minus a 0. I still have the same 20. And now I can move down my list to 16. So how many 16s are there in 20? There's 1. So I've got minus 16, gives me a leftover 4, which happens to be the next number I'm working with, right? 4. So how many 4s are there in 4? 1. What's 1 times 4? 4. And what's 4 minus 4? 0. But we are not done because we always divide by every number and we still need to divide by the number 1. Now, how many 1s are there in 0? 0, right? So I don't really need to do anything exciting or anything to get that, but that 0 is part of my answer. Your answer is this list of numbers. It's 2, 2, 3, 0, 1, 1, 0 with a subscript that says 4. Okay, we have one more. Same process. We have 99,999, and we're going to put it into base 9, where there are no 9s. And you can't just swap them all out either. It doesn't work like that. It's not that friendly. We need to know powers of 9 in order to do this, just like we did powers of 4 on the last one. So I've got the 1s place, the 9s place, and then 9 squared I know is 81. What is 9 cubed? 729. Okay. And then what is 9 to the 4th? Okay, and then I need 9 to the 5th. What's 9 to the 5th? Okay, and we'll go ahead and do 9 to the 6th. It's going to be too big, but what is 9 to the 6th?
500. $40,441.
Say it again for me.
That's wrong.
I don't have this one written down, so.
531,441.
Oh,
Isn't that what you said?
That's what I said, okay.
Okay.
You're right.
Okay, cool. All right, and that's clearly too big, right? Our number is 99,000. This is 531,000. That's way too big of a number, so we don't need this one. That tells us we're ready to stop, and we're ready to do the division with those values that are powers of 9. So we're going to start by dividing by 59,000. $49. And how many 59,049s are there in 99,999? Is a really good question. It's a really easy answer actually on this one, huh?
Only one.
There's only one. There's only one of them.
Oh.
So 59,049, we'll subtract. What do I get when I subtract those two?
$40,950.
That's right. And so we've taken care of the first division. Now we will divide by 65, 61, right? So how many 65, 61s are there in 40,950? 6. Okay. What is 6 times 6,561?
39,366.
Lovely. And we will subtract. What do you get when you subtract?
1584.
It is. Okay, so we've divided by the 65, 61. Now we'll divide by 729. So how many 729s are there in 1584? 2 is right. 2 times 729 is 1458. And again, we subtract. What do we get when we subtract?
126.
Uh-huh. All right. Did the 729. What will we divide by next? 81's next. How many 81s are there in 126? 1. So we'll subtract our 81. And when we do that, we get what?
45.
45. And what will we divide by next? 9. 9. Whoops. 9 goes in 5 times. 5 times 9 is 45. Subtract and I get 0. Am I done? No. What do I still need to do? Divide by 1. It goes in 0 times still. They don't always go in 0 times at the end. These two just happen to. But the beautiful thing about this algorithm is that your answer, of course, is all just right here. So this is 162150. And then down here you write base 9.
Should it always, like at the last step, should it always end in like 0?
It will not always end in 0. No, and I'm actually glad you asked that question too, because there's something else that kind of should mention here that you should be aware of is how many numbers did our original number start with on this particular problem? Like how many numbers are there in 99,999? There's 5. How many numbers are in the one that I end up with as an answer? 6. So if the base is smaller, there's more digits because you have fewer digits to be able to use, right? So if you're turning it into a smaller base, you better get more digits at the end than you started with very few exceptions. And only exception would be as if they happen to have the same number of digits, but that's rare. Okay, so if it's got, like it happened over here too, right? The number was only 5 digits, and how many do we have at the end? 7, right? The digits become more because we have fewer digits that we have to work with.